Okay, so let's see, why does this violate the third law of thermodynamics?
Ground state doesn't have energy. And T is zero.
No, ground state doesn't have any energy. No, the ground state energy, we can always fix it to 0. So what is the third law of thermodynamics?
What about how many configurations we still have? If we don't have just one configuration, then we require less configuration.
You see, okay, so let's, in the thermodynamics doesn't know about the microstates. Still, that expression violates the third law of thermodynamics. That is why that cannot be correct. What was the third law of thermodynamics? Entropy should go to 0. Let's see as the entropy as a function of temperature and volume. And entropy should go to 0 anyway. Whatever the volume or the pressure or whatever other variable you have. How did we define the... So what is the specific heat at constant volume? Okay. The definition was dq by dt at constant V, which is dq is just TdS by dt at constant V. Well, that the entropy goes to 0 basically tells me that STV is equal to T to some power times some function of V. Delta should be a positive power. I don't know what that is, but at low temperature, that should be the form of the entropy. So the form of the entropy, you see, if I just put it over here, it should be T delta F of V T to the power delta. As T goes to 0, the specific heat as T goes to 0 goes to this number, this form. But keep in mind delta is positive, so this goes to 0. So specific heat, the third law of thermodynamics tells me that the specific heat at constant volume should go to 0 as well. Well, but this expression already tells me that the specific heat at constant volume is 3/2 NK. It doesn't go to 0. So even for the ideal gas, this expression should be modified at low temperatures. And the modification will depend on whether it's the fermions or bosons, etc. The third law. Now, of course, the ideal gas law doesn't, it's not valid. We already know that it's not valid at very low temperatures. But we will see the modification due to this one. Now your question.
From the last section?
Yeah.
Yeah.
I mean, if you don't have any other questions for the time being.
It's not exactly a question, but we had container in the last section, I believe, and we opened the hole in there, and just by particles
Escape.
escaping from the soil, the temperature is decreasing in the system.
Mhm.
It seems weird.
Where was it?
The fourth section, 6.4, I think.
Yeah, these are your
7.
midterms. That is still chapter 5. Where? Why do you say that the temperature is decreasing?
Just at the end, when he's talking like particles that have a speed larger than u, then there's a runoff energy.
Well, essentially. Hmm? You see, the basic idea is if the high energetic particles will escape more. Yeah, so they are carrying away more energy. Now, the remaining particles, when they equilibrate, they will have a lower temperature, lower energy per particle.
So when the particles are moving, the system is not in equilibrium.
Sure. You see, escape process is not actually an equilibrium process. And since on the average the escaping particles have more energy, because more energetic particle will escape more than less energetic particles. Per unit time. You see, the basic idea over there is, let's say, if you have this condition in a given time dt, now slow particles within this volume will escape, and more energetic faster particles within this volume will escape. Since they are moving faster, they will reach the opening in the same amount of time. But then we are taking more energetic particles from a larger region in my system. Well, there are more of them. Since the region is larger, I have more energetic particles. So a small portion of low energy particles, but a larger portion of high energy particles is escaping my system. The remaining system will not really be equilibrium because it doesn't have this Maxwellian velocity speed distribution anymore. But it will equilibrate in a very short amount of time. So eventually we can still treat them as equilibrium systems. But when they equilibrate, on the average, they will have a lower energy. But
Can you repeat the part when can we treat the system as an equilibrium?
you see, this system, if you can follow the system instantaneously at every moment, it will not be an equilibrium system. But how do they equilibrate? Well, they will equilibrate when a sufficient amount of time has passed such that there are many collisions between the particles that are not in equilibrium and the particles that are in equilibrium. There should be many collisions between the particles. After many collisions happen between the particles, the energy will redistribute itself so that we will reach an equilibrium configuration. Well, how long does it take for many collisions to take place among the particles? With respect to what?
How fast?
How fast they are moving, yeah.
Sound escape.
Well, the speed of sound is quite fast. So on the average, we can still treat the system as if it is in equilibrium at every instant, assuming our resolution of time measurement is not very fine.
But still, you can have certain types of fluids which have the appropriate plane of sound, for example, such that the system is not in equilibrium.
Sure. But even in that case, you can treat them as locally in equilibrium, so-called the quasi-equilibrium systems. Locally, you can always define an equilibrium state. You can define a local temperature, a local pressure. Yes, for flows, for example, you can create flows where the temperature will not be uniform. So on the whole, the system is not in equilibrium, but if you take a very small portion of the system, that will be in equilibrium, and hence you can define a temperature. So you have a position-dependent temperature.
So people do stuff like competition fluid dynamics.
That's what they are doing. Yeah, they treat, when you do fluid dynamics, what they do is they treat the system as if they are locally in equilibrium. There's a local temperature, there's a local entropy density, there's a local mass density or the number density, etc.
And their local region in equilibrium would be 1 pixel voxel.
Hmm?
So they treat certain local regions in equilibrium. So that local region is it something like a pixel in their simulations?
Okay, that will be the details of the simulation, I don't know. But physically, what should happen is, you see, you can take a very small region. For example, here, this is not an equilibrium system. The temperature inside is different than the temperature outside. But any significant change in the temperature will only appear, I don't know, let's say within 1 millimeter. That's a reasonable assumption, right? A reasonable temperature change appears in 1 millimeter. Then the question is, how many degrees of freedom are there within that 1 millimeter? It won't be maybe 10 to the power 23, but it will be, I don't know, 10 to the power 15. That is still a huge number. So that is still large enough so that we can use statistical treatment and thermodynamics, but small enough for any significant change in any of the thermodynamic properties. So in such systems, you can still treat them as locally in equilibrium. You see, using these similar treatments, for example, you can also discuss the photoelectric effect. What happens in photoelectric effect is you again have a gas of electrons. They collide with the surface, and they can escape if they absorb the photons. Or thermoelectric effect. When you heat a material, it emits electrons. For example, the electron guns used in accelerators or various other equipments, or the X-rays, if you have ever taken an X-ray. What they effectively do is there is an accelerating potential, but they also have an electron gun, which is just some resistor, usually made of tungsten, and they pass a large current through it, which is heated up, so it starts emitting electrons, which are then accelerated through an accelerating potential. But there again, you have a heated gas of electrons. Some of them will hit the surface. If their energy is large enough, they will just like in this problem, they will just escape in a given direction. And then you can calculate by knowing the density of the electrons. No, we already know, we will discuss their speed distribution. We know their energy distribution. We know how much extra kinetic energy they should have to overcome the potential barrier of the metal. You can calculate how many electrons you will get at a given temperature. It will be exactly the same problem. They do. They are, I mean, in a given metal, they do behave like almost free electron gas. Now, when we discuss fermions, we will see that the electrons have, in fact, a huge energy. And since they have such a large energy, the potential energy of the system will be small. The potential energy of interaction. In most purposes, not all the time, but in most purposes, we can treat them as if it's small. Approximately, they do behave like an electron gas. Yes, other questions? So why does it invent this concept of cells?
Easy.
Why?
You can directly see the relation between G and N. Makes it obvious to treat
Really?
the system better.
I mean, when I was first studying this book, I found it kind of confusing. Why it invented these cells with G, whatever that G was.
But these several lasers are not really each one of them related to a certain phase of my system.
Phase? No, there are no phase transitions here. No.
I think it makes sense if there are degenerate states,
Are they degenerate?
or if the energy levels are continuous, G is similar to density of states or something like that.
Yeah, it is similar to density of states, but are they degenerate? Are they continuous? What is the spacing between the energy levels in a macroscopic system? How does it depend on the size of the system? So how does the splitting between the energy levels depend on the size of your system, typically? The exact dependence will, of course, change from system to system. For example, in the particle in a box, 1 over L squared, which is, if you take L to be cube root of V, V to the power 2/3, 1 over. Okay, if you don't have a relativistic particle, but if you have a non-relativistic part, if you have relativistic systems, the power will be different, but still it will be 1 over the volume to some positive power. That will not change. So for macroscopic systems, the spacing between the energies will be negligible. It's almost continuous. Well, since it is almost continuous, instead of sums, you have integrals. Well, this treatment will be somewhat more complicated if you stick with integrals. So he just divides it into cells, so that he writes summations over cells or products over cells. That is one thing he does. The second thing he uses is that this GI minus 1, he assumes it to be large, so that he just uses Stirling's approximation. It just simplifies the computation. It's not necessary, but as the book states it simplifies the computation. And as you have pointed out, it's essentially the density of states. You see here, This alpha is what turns out to be the chemical potential, so that we impose the constraint that the total number is fixed over here. If the total number is not fixed, then we don't need alpha. Like in the case of the photons or phonons, where their number is not fixed, then their chemical potential is just zero at all temperatures, at all volumes. So you see here it makes the treatment in the canonical ensemble and then goes over to the grand canonical ensemble. Last questions? Yes. I mean, in the week of the homework, I mean, while you are taking the homework, you don't need to worry about the. While you are taking the midterm, you don't need to worry about the homework, but you will still have homework. And before, I mean, the pre-report will definitely include the next 4 sections. It might be more, so if I forget to upload it early, you already know part of the pre-report. And see you on Wednesday.